In this chapter, we're going to focus on finding limits in pre-calculus. And limits kind of serve as our foundation for further endeavors in calculus. And they're kind of a bridge that we can bridge between pre-calculus and calculus. So in this video, we're going to be finding limits numerically. In the next video, we're going to be finding limits graphically. So looking at the standard form problem, standard form for a limit, we have the limit of f of x as x approaches c is equal to L. Okay, so what do all of these mean? L is going to be our limit. Most of the time, this is what we're trying to find. This was usually the solution, what we're trying to find. In this case, we're trying to find limits using the methods of numerically and also using graphs to help us find the limit. And there are also other methods to find limits, but right now we're going to focus on these. So the limit is what we're trying to find. Okay, f of x is just a function. This could be a linear function, it could be a rational function, it could be a square root function. It's just a normal function that we dealt with throughout the year. And then finally, this is going to be, we would say, as x approaches a constant c. So c is going to be a constant that x is going to approach, and as x approaches c, we will get this value, L, which is going to be the limit. Okay, so let's dive into a problem so you can kind of see how this whole thing works. So we have a normal linear function, good old linear function. F of x is equal to 5x minus 3. Okay, so what a limit is a limit describes the behavior of a function output when c is inputted. So what this is basically just a fancy way of saying when we input c, or when we input values that are very, very close to c, they will approach a value L, and the L is going to be our limit. So if we have our linear function f of x is equal to 5x minus 3, we're going to use a table to find values that are nearby and thus evaluate the limit. So making our table, we're going to have we're going to have x, we're going to have the output of the function, input and the output. And we're trying to find the limit of f of x as x approaches the value, in this case, we're going to have 3. So we're going to have 3 over here, and then we're going to find values that are less than 3. We're going to find values that are slightly greater than 3. So we have 2.9, 2.99, 2.999, 3.001, 3.1, and 3.1. I just pick values that are very, very close to 3 and are slightly bigger. We're slightly getting bigger with each value. So we can kind of observe the behavior of the graph in this general area. So we can just use a calculator and plug in these values for x and see what we get. And if we do that, we get 11.5, 11.95, 11.995, 12, 12.005, 12.05, and 12.5. So we can see that as we approach the value of 3 from both sides, we're slightly getting towards closer and closer to this value of 12. As we come from the left, we're just getting 11.5, 11.95, slightly closer and closer to 12. And same with this side, we're getting slightly closer and closer to 12 until we hit the value of 12 at x equals 3. So you're probably thinking, why didn't we just input the value of 3 into our function and use the output to get our limit? The process that we have here, where we input this value 3 and the output is the same as the limit, is called direct substitution. And direct substitution doesn't always work, but in this case it does. And the cases where it works is all polynomial functions. And what is a polynomial function? Well, a polynomial function is where we have a function of x, or any variable, where the x is 1, the exponent for x is going to be 1 or greater. So we can have linear functions where it's x to the 1 or x. We can have quadratic, which is going to be x squared. We can have cubic, which is going to be x cubed, and the list goes on and on. What we can't have, however, make that in red, what we cannot have is we can't have rational functions. Rational functions are going to be x to the negative 1 or 1 over x, or some sort of play on this basic unit we have here. And we'll use a rational function right now to see why we can't use direct substitution when we're trying to find the limit of it. So we have the rational function f of x is equal to x cubed minus 8 over x minus 2. So let's investigate the behavior near x equals 2. So we need to approach it from the right and also the left, just like we did in the previous problem. So I'm going to make another chart. The input, the output, I'll kind of label that here. Input, output, and the value we're trying to get to from both sides is going to be, in this case, again, we're going to find the limit of f of x as x approaches 2. So our big value over here is going to be 2. And then from both sides, I'm going to use values that are slightly smaller and slightly bigger. So we have 1.9, 1.99, 1.999, 2.001, 2.01, and 2.1. Again, we can use the calculator to find out the value, the output, for each one of these inputs. And what we get is we get 11.41, 11.94, 11.994. At 2, however, what we have is we have undefined. And the reason for that is if we put 2 in the denominator, 2 minus 2 is equal to 0. And anything divided by 0 is going to be undefined. So the function is actually undefined at the value x equals 2, which means that when we have our graph, which looks something like this, we're going to have a hole at this place x equals 2. So if you have 1, 2 units, this value is going to be undefined. The graph actually stops, and there's no value at that point, and the graph continues again. And that's what the graph generally would look like approximately. So we'll talk about that later, but let's continue on with our chart, our table. So for 2.001, we get 12.006, 12.006, and finally 12.6. So we can see that even though the value is undefined for x equals 2, we see that we're slowly inching towards the value 12 from both sides. We're slightly greater than 12 here, and slightly less than 12 here. And if we find the average of 12.006 and 11.994, we get the value 12. So what that means is that the limit is equal to 12. We do have a limit, even though the function is undefined. So the important property we just learned here is that the function doesn't have to be defined at x equals c to have a limit. So this is also the reason why we couldn't use direct substitution just like we did in the previous problem, because if we look here, if we use direct substitution for this particular problem, we would be substituting 2 into this function, which would give us the value 2 cubed minus 8. So 2 cubed is 8. 8 minus 8 is equal to 0 over 2 minus 2 is 0. And 0 over 0 is a undefined value. And therefore, we can't use direct substitution to find the limit of this. And one way to find the limit would be to make a chart to find this. So that's why direct substitution really only works for polynomial functions, functions that are continuous. Continuous. This particular function has a hole in the graph where x equals 2. But if we have a linear function, we're going to have a line. If we have a quadratic function, we're going to have a parabola. And if we have a cubic function, it's going to be like that. And the function is always going to be continuous. There are no holes that are going to be present in the graph. And that's why we can always use direct substitution to find the limit of that particular function. However, we can't always use direct substitution here because these functions tend to have holes and asymptotes and stuff like that that will give us a value that's undefined. And because of that, we won't be able to use direct substitution.